Good afternoon, everybody, to those here and also to the SAB members and others attending remotely. I will speak about the Dynamically Driven Application Systems program, which... Well, I've moved this. Can you hear me better now? So the efforts that are supported under the DDDAS program are aimed to develop capabilities, advanced capabilities for modeling, analysis, understanding, and control of complex systems, be they engineered or natural. These new capabilities are going to be developed through an approach which dynamically integrates the computational aspects of a system with the instrumentation aspects of the system. The portfolio, in terms of the research directions in the program, supports new ideas in new modeling approaches, application modeling, application algorithms, instrumentation methods, and system software to support the dynamic runtime environments in DDDAS application systems, whereby the computational aspects of the application are unified with real-time data acquisition and control aspects of the system. This is a program that was announced about a year ago, and projects are awarded at the end of FY11. In this presentation, I'm going to give an overview of DDDAS and the background on DDDAS to motivate the need for the research directions in the program and also the need for multidisciplinary research. And then I will give some examples of efforts that are funded. So what is DDDAS? With DDDAS, we want to move from the static triad of modeling systems, the theory, modeling, and experimental probing into a tightly coupled, dynamically coupled relation between an executing application and the measurement instrumentation process of the system. In the sense, as the application executes, data are integrated into the model to improve the modeling process, and in return, the model controls the instrumentation process to collect additional data, and this is repeated in a feedback loop. So the idea is compelling. There are many challenges because in this case, the application models need to interface with the measurement systems and integrate dynamically stream data. Also, the application models can invoke other modalities, models of higher levels of fidelity in specific regions of the phase space of the problem. We also need capabilities for algorithms that are stable under perturbations from the stream data, and also computing system support, because the these application environments involved high-end platforms all the way integrated to the real-time data acquisition and control. So we need system software that can support these dynamic and heterogeneous environments. The need for multidisciplinary research is a key across these four axes. The idea has been considered compelling. And also, although I've used the mathematical term DDDAS, I've also introduced the term infosymbiotics. Although the community seemed to like DDDAS, they consider it part of the vernacular and trademark. So here I, in a sense, show some of the capabilities that are enabled through DDDAS. The ability of speeding up the simulation by replacing parts of the computation with actual data, or the ability of improving the model by replacing or by complementing aspects of the system that are not captured in the model with the actual data. Also, one can use the dynamic data to extrapolate between full-scale solutions in the phase space of a problem, and thus create decision support systems with the accuracy of a full-scale simulation. And I will give examples in the projects that I found from all these cases. In terms of the instrumentation, the idea of the application controlling the measurement process creates more efficient measurement processes. And also, an important aspect is, which is a big challenge, we need to have ability of managing heterogeneous assemblies of sensors. This is a big challenge. I'm going to discuss this a little bit more later. And the idea of having the application model controlling this heterogeneous assembly and scheduling the resources, the sensor resources, is important. And the same, of course, is for networks of heterogeneous controllers. Somebody has said, computational science or computational modeling is the third paradigm. Somebody said data is the fourth paradigm. I call DDAS the unifying paradigm for the reasons that I discussed earlier on in terms of unifying across the spectrum of platforms and unifying the computational and instrumentation aspects of a system. So I spoke a little bit about some of the challenges. Here are some more. We talk about, today, multi-scale, multimodal modeling. In DDAS environments, these multiple scales, multiple modalities may be invoked dynamically at runtime based on the dynamic inputs, or switching to different algorithms depending on the dynamic inputs. And again, I'll give examples. In terms of algorithms, we need algorithms that are stable and with good convergence properties under perturbations from dynamic data. And also we need methodologies and more efficient methods for handling data uncertainties, uncertainty propagation and quantification in cases, for example, not only within a model, but also with dynamic invocation of models, as I described above. And actually, many years ago, I funded the work of generalized polynomial chaos, and also one of the projects under this current portfolio also have developed some fast uncertainty propagation algorithms. In terms of the measurements are collected in many modalities from multiple sources, different data representation, different formats, and we need to, in a sense, interface these to the modalities, the data models and of the applications, and that relates, in a sense, to the interface of the measurement systems. In terms of system software, we need to have capabilities of dynamic runtime support of these environments. I will discuss in a minute of how motivating it from the computational grids that we addressed for a number of years ago, which also provide heterogeneity of the underlying platforms and dynamicity of the resources. I've started funding some work that now is making significant impact. In DDS environments, the bar is raised a little higher because together with the computational grid, we bring also the instrumentation platforms. So why DDS is timely now more than ever is because for a number of recent scientific and technological trends and advances, and these include the need that we need now to model ever more complex systems, actually systems of systems. And I will give examples of that in some of the projects I found. And also that has, of course, given impetus to more, in a sense, many efforts in application modeling, multi-scale modeling that I mentioned is one. Together also with these drivers, we have also the onset of ever more powerful computational capabilities, and now in the context of multi-cores, and I will discuss later the importance of the multi-cores in the DDS environments. And at the same time, of course, networking bandwidths have also increased in unprecedented sort of levels, and that's important for the ability of streaming data into an executing model. The other is a sort of trend that is also significant is the ubiquitous censoring, sensors everywhere. And in some ways, many years ago, when we embarked in the sort of parallel computing concept for increasing sort of computational capabilities, that was considered as a huge challenge, the attack of the killer macros, it was said. And I believe now we are, in a sense, have what I call attack of the killer macros wave number 2. In this case, the macros are actually the sensors. But also, of course, that became an opportunity. Parallel computing gave us sort of the rise of the unprecedented computational capabilities we enjoy today. I believe sensors are also an opportunity, ubiquitous sensoring, because it can help us, in a sense, design ever more smarter systems. And of course, addressing the challenge, DDAS provides approaches that can help us manage this challenge and exploit the capabilities. So in this slide, I would like to discuss a little bit why multi-cores also are very important for DDAS. As I said, for a number of years, we dealt with grids, computational grids, where it's included an array of heterogeneous platforms. Actually, the high-end platforms, they each have multiple levels of processors, hierarchies, interconnects, and so on. So they are like also grids in a box. So there has been, for a number of years, a major challenge of how to, in a sense, create a runtime environments for these either the high-end platforms or the assemblies in the computational grids. And I started sort of funding work in these areas to address these challenges, motivating from the fact that the underlying resources in these environments are dynamic and adaptive. In DDS environments, of course, the application requirements themselves are also dynamic and adaptive. And moreover, in DDS environments, we bring also the instrumentation grid. So the heterogeneity in DDS environments is increasing beyond sort of that we encounter in computational grids. So now with multi-cores that are populating all levels of these kind of platforms, but also are populating from the high end to the mid-range, to the instrumentation platforms, to the end user kind of devices, the challenge of this kind of integration across this heterogeneity that is required in DDAS, I believe one at least level of complexity is squashed a little bit because it will be the same kind of multi-cores populating this range of platforms. And I want to give an example of why this is important in terms of the compiler directions that I pushed a number of years ago, where I pushed for the compiler as the layer for enabling this dynamic adaptive mapping that we needed in computational grids and also we need in the DDAS environments, and how a project that I started now has panned out. This is a project that I funded. It's a career award to Vikram Adve from University of Illinois. The project developed fundamental ideas that were, in a sense, pursued in 2000, have created now the LLVM, the low-level virtual machine compiler and compiler infrastructure, which is, has been installed in a wide range of platforms, and in fact is replacing GCC. GCC has been, for the last 25 years, the workhorse for compiler infrastructure. Moreover, LLVM is installed in the high-performance machines Jaguar is one of the highest performance machines in the US and the world. And also, as we move into the exascale, LLVM also is used in one of the prototyping efforts. So the idea that we have now a capability of an infrastructure that we can use across all platforms shows that this dream of mine, or what I had articulated, the need for dynamic integration across this heterogeneity, is feasible. Where we are and where we are going, Kvovadimus. Through agency programs, we created a number of ideas and advances that are needed for DDAS. I like to say DDAS requires advances across multiple S-curves, and through programs that included synergistic multidisciplinary research within sub-areas of computer science in the NGS program and several other programs that I managed at NSF, together with programs that involved also other fields together with computer sciences, and programs, of course, in other agencies, are creating quite a bit of the advances that we need, and together with the trends that I mentioned, in terms of multi-cores, sensors, and so on, we create sort of a situation where we have now we're climbing a little bit on the steep side, and I think we will be able to make progress in accelerating ways. I want to give an example of the impact of the DDS program that I had started at NSF a few years ago. This was a multidisciplinary program, included all the NSF directorates, included several other agencies, And I've funded work that covers all these areas that I have here. And I think that's important because that's created also a broad community of DDAS researchers that now can be brought and contribute to the AFOSR efforts or the program that I have here in the AFOSR. And also, these are some nice comments that have been made about DDAS by important people in the scientific field. We also had a multi-agency workshop, and I'll talk about that later. In a sense, considering now the impact of the DDAS in the interests of the Air Force, the Technology Horizon report, a 20-year vision for the Air Force, identified these top key technology areas, and DDAS is relevant in quite a few of them. Somebody said key, actually, constant. So now I will discuss a number of examples from projects that I funded. They range from structural health monitoring of systems, and actually at several levels, and to decision support system for aerial platforms, to agent-based simulations, to object tracking, moving object tracking, to volcanic ash propagation. One can say that the projects I'm going to show you vary from the nanoscale to the terascale, tera with 2 R's. So here is the project, the first project, which looks at modeling methods to detect damage and predict the evolution of damage in composite materials, anisotropic composite materials. The test case is composite material integrated with a carbon nanoparticle sensor lattice. And when pressure is applied in the material, changes the resistivity. The microcracks that are created because of the pressure, the damage, changes the resistivity. So by observing the current, one can, through an inverse lattice percolation model, one can translate the change in resistivity into the microcracks field. That microcracks field is now incorporated into the damage model. And in the next, here shows the DDDAS loop. So one thing, in addition to, in a sense, remeshing the damage model to represent the microcracks, also the Young modulus of the material changes and other parameters, but the Young modulus, for example, changes. So we need to, in a sense, calculate through a Bayesian inverse from the percolation model the values of the Young modulus. Of course, there's uncertainty, so actually these data are coming in a probability distribution function, and the damage model produces a prediction or an assessment of the damage also as a probability distribution function, and that is used again to drive additional measurements of the electric current in a DDDAS loop to assess more accurately the extent of the damage, or as additional pressure is applied, the evolution of the damage. One thing to note is that this is a multidisciplinary team, and as are all the other projects that I'm going to show, bringing together materials modelers, math and statistics, and experimental material sciences and computer sciences. The previous model addressed sort of damage assessment at the micro scale. This project is also addressing damage and health assessment in structural health assessment, health monitoring is the term used for at a larger scale, namely buckling, delamination, waviness, and disbonding, for example. The case study is the flat part of a blade of a rotor in a helicopter. The models involve structural models as well as fluids to, in a sense, model also the stresses on the system because of the turbulence flow. Here's an example of how DDS is applied in terms of the structural model. This is the mesh in the initial condition, which is used by the structural health monitoring model. Sensor data are entered into the model as waviness, for example, is detected. The computational mesh is revised. New data are collected in a feedback loop, so one can assess either the full extent of the damage or the evolution of the damage. And for the brevity of time, I won't show the next example. As I said, these are computations which are coupled with the fluids. So as the material shape, for example, changes, the boundary conditions, this thin layer approximation mesh needs to be remeshed. And the coupled fluid structural modeling computation occurs. And this shows the sort of the assessment loop where we can predict, for example, as I said, the assess the damage or predict the evolution. This modeling also can be used for mitigating the damage. For example, if you have actuators, you can take actions where it's counter sort of the damage, or take actions that adjust the operation. In this next slide is shown sort of the full computational workflow for this modeling effort. Includes the structural modeling, the regridding, the coupled CFD FEM modeling, and also other modeling, for example, sensitivity analysis to assess the health condition of the system. This next project is developing capabilities for autonomous mission planning with when the air vehicles that are cognizant of their own state and also the state of their surroundings and respond accordingly and intelligently. So this involves this task, infer the state of the system, predict the other constraints, for example, other aspects in addition to the area platform itself, for example, environmental condition, and use that to replan the mission. DDAS is used in all this, and also in specific modeling approaches used, the wealth of modeling approaches used to do this the modeling of all these phases. And I will give some examples next. One thing to point out is like the other computations, multi-fidelity modeling is done where you, for example, you have high fidelity models that may be done offline and may be invoked at execution at the operation time. And I'll show examples of that too. So here is an example of how DDS is applied, for example, for the surrogate modeling approach. In this method, full-scale solutions are used to calculate a specific point solution in the phase space of the problem. And then the state of the system is extrapolated through approximate functions called surrogate models, which of course have an uncertainty. And now during the operation of the system, this region of the problem is important. So we use DDAS to stream data from the sensors online. Says one datum here, but maybe more in a feedback loop. So to collapse the uncertainty, for example, because you want this higher fidelity information from that part of the phase space. The other aspect is, the other example is structural damage. This is the computational mesh of a part of a wing. Sensors detect damage in these two places, and the computational cells are removed and the data are replaced by the sensor data, as per the examples I gave in the beginning of the use of DDAS. As the sensors detect further damage, other additional cells are replaced with the actual sensor data. The sort of software framework or the modeling framework for this project is shown here. As you can see, there are several stages of modeling. First of all, DDS is applied in all of them, as I said earlier on. But also, this is the workflow for the health assessments, which is analogous in a sense to the one I showed for the previous project. And we have sort of sub-workflows in all these. So based on health assessment and also other information about the vehicle, the information is fed into the planning models that also measure environmental factors. And then estimates of the condition of the vehicle, flight limits, and mission plan are produced. As may be needed, more accurate kind of estimates are required by each one of these phases. And so the bigger DDDAS loop, in a sense, is launched. I have much more information in each one of the slides, which I included for the benefit of the SAB, but I don't have time to go through all this. So the next project is a project that is going to build an agent-based simulator for swarms of UAVs. The case that we have to deal with a multitude of UAVs and also multiple classes of UAVs, so there is heterogeneity and at the same cooperation that is needed in the missions. Make sort of the current model of an operator per UAV or a group of, or a team of operators per UAV, non-scalable approach. So there is, in a sense, interest of developing automation tools, and this is an example of the multi-UAV tool that has been developed at RB, the Vehicles Directorate in Wright-Patterson. This simulator is represents, in the simulator, represented certain static attributes of the air vehicles, of the UAVs, also certain missions that the UAVs may take. But this is quite a bit hardwired. Also, it's scalable to 20 UAVs for real-time or near real-time. So we need to develop much more simulations that are able to represent many more attributes of a system. For example, you can envision such a simulator to be a back end of the previous projects I described. And so this is the focus of this effort here. On one hand, to develop a much more flexible and robust simulation, age-based simulation model, and at the same time, which will be in a sense driven by sensory input from the sentient world around it. In this case, for the project, the test case, this data will be synthetically generated by the multi-UAV simulator. And the other second part of the effort of this project is to also address the software engineering requirements for simulators that are dynamically driven by inputs and also dynamically may invoke other modalities, other behaviors of a UAV or the surrounding environments. The next project is using DDDAS to enhance the capability of tracking a moving object in cluttered environments. In these cases, for example, where there are occlusions or shading, typically one wants to have multimodal sensing, and one wants to use, in a sense, the right sensing for when the object is in a certain, for example, under shadow versus in sun, or for example, here is in the desert versus more urban terrain. So the project is going to use DDDAS by adapting the sensing modality driven by a model that predicts where the object is moving. The data, again, for the modeling are synthetically generated by the DRSIG, which generates actually pretty realistic scenery, and also models for tracking people and vehicles movement. This is the DDDAS Loop. The sensor actually is created by another project here at AFOSR, Dr. Kit Reinhardt. It's a multimodal sensor, hyperspectral and polarization imaging, Fabry-Perot interferometer. The forecasting model starts from some initial conditions, tasks the sensors, data are collected, the data are integrated in the forecasting model. They're correcting the model when they differ from the model, or they augment also the accuracy of the model, and then this loop is repeated. There are other functions that are taking place here. For example, assessing the readiness of a sensor to switch that given modality, negotiation of sets resources, and so on. And of course, there are multiple sensors that are being tasked. This project is developing enhanced capabilities for more accurate tracking of volcanic ash. We know that such events can be highly disruptive for air operations. The notorious one is the Icelandic volcanic eruption, which shut down the Northern European air system for many, many days. And because, first of all, the predictions over-predicted regions where the ash propagates and actually under-predicted, so they miss some regions. The reason such models have these errors is because there are errors in the observational data and uncertainties. And this project is going to use DDAS to handle errors and uncertainties in a way that is much more comprehensive, and also the modeling, so that the errors are not, in a sense, affect the integrity of the computation. This is the modeling workflow of this project. The volcanic ash observations, because of uncertainties, of course, probability distribution function is generated, is input into the bent model, which is modeling the volcanic eruption in the region of the volcano, and that generates input data. Each one of these columns becomes an input data to the transport code PUF. Wind data also are incorporated into the PUF model. And because we want fast ways of uncertainty propagation, the project is using an algorithm developed by the PIs, the polynomial chaos quadratures. One thing to note is, so the output of this combined coupled PUF bent model is also used in an inverse Bayesian to select data that are collected from satellite imaging tracking the volcanic ash. And one thing to note is that when the PIs started some of their preliminary runs of the model, they discovered, they pointed out an error, the computations pointed out an error in the analysis imaging that of the satellite data by the analysts. In fact, it did not, the analysts missed a region where the volcanic ash spread. So this is a case of DDAS in some ways is used to correct the errors of the or the analysis of the observational data. So anyway, the correct errors, the correct data are also again input into the PUF model, integrated in a DDAS into the PUF model, and this can loop, in a sense, can the DDAS loop can continue. Also, data are also in an inverse Bayesian, the parameters at the site of the eruption are also improved, and also that sort of loop, in a sense, continues in that way. A year and a half ago, we had a multi-agency workshop. It was sponsored both by AFOSR and NSF, and included also several other agencies. Produce a report that I've gotten very nice comments about it, and it's in this website. This is the logo. And in terms of outreach, I've given a number of presentations over the last year, including in external forums, including also the labs. In this June, we have a workshop/PI meeting plan. My strategy always has been to organize the PI meetings around a conference or a workshop, because in addition to the PIs, we draw also attendees from the broader community, and not only more people learn about the program and about the projects, but also ideas leveraged both in both ways. Also, for proposing this, the DDAS concept, I was recognized myself from the IEEE last year. So some other programmatic directions and interactions. These are new projects, but already we have established some collaborations with Air Force Labs, the Mobility Command, and the Propulsion Directorate, and also this project with the Air Vehicles Directorate. And as I said, we also leverage other programs here at AFOSR. In terms of research trends, I think the 4 axes of research will be equally emphasized. The projects that I described, they also have considerable work in the system software area for runtime dynamic management. But also I hope that we also use these projects as drivers for some more work on dynamic runtime support, exploring, for example, some projects by Paul Fautrier in France. So let's see, and also some projects that will maybe develop complementary or additional approaches along some of the projects already funded, and also explore other areas. And again, there is interest by other agencies, and we'll look into, in a sense, building on these collaborations. And with that, I thank you for your attention. Any questions?
Okay, questions? Anybody?
To what extent on the volcanic ash, it makes me think more about weather modeling.
Mm-hmm, yeah.
To a certain extent, were you able, for example, to do something that would take a normal weather model, which I'm sure was being used and compared with the models that you were doing? I was one of the people who ended up spending a week in Europe as a result, so I'm interested.
Oh, lucky you. So actually, yes, we have done that. In fact, in addition to the PI of this project, I have introduced Dr. Erbschlau with Kelvin Drogemeyer, who was funded by the big lead project at NSF. I never gave a penny to Drogemeyer, but he told me that he became enamored with DDAS and he adopted it. So I always use it as an example, because when you don't give anybody some money and they really like your idea, that's very genuine. So yes, we have, in a sense, creating more, in a sense, faithful modeling of the ash propagation through more adaptive weather sort of monitoring, and also more predictive models. So DDAS also is used in this by Kelvin Drogemeyer. And I think Dr. Erbschlau is somewhere here. Okay, right. So definitely.
Any other questions? All right, let's thank our speaker.